We're now going to run the exercise. Actually, it's not an exercise, it's a demonstration. The notebook number 1, which is the first light example with Ascent. So it's really one example from top to bottom, or from bottom to top of the interface. So my very first cell will be import conduit blueprint, and then import Ascent. The reason for importing blueprint is to verify that we have encoded our data in the proper way, okay? So that it follows the convention of usage. So I will run my first cell, and then I will create, in cell number 2, I create my first mesh. So I declare a conduit node, and then I pass this node to this particular function, which will create a mesh, an hexahedral mesh of size 50, of resolution 50 in all 3 directions. And now that I have run the cell, I can actually print that mesh, just like that, okay? And it follows, we can tell already that it follows the convention of usage. This mesh object, okay, has a state with an iteration number and a time value. It has a coordinate set which is explicit because we have hexahedral, with an X, a Y, and a Z array. It has a type unstructured. The shape of the element is hexahedra. It has a connectivity list, which, if you are using finite element coding, you will be familiar. This is the connectivity, this is the relation between cells and vertices. And in the fields category, we have one name, bread. That's actually the name of the variable. It's associated with the vertex, and it is an array like we've done in the previous example. We have a second variable called radial, and this time the association is with the element. And then we have, interesting, a velocity field, a vector field called vel, and it has 3 components, the u, the v, and the w component of the velocity. So this is our mesh. I will now go to my third cell, which is to initialize Ascent. So Conduit is the API to define your meshes, but Ascent itself also uses Conduit to specify its own interface. So as you see, to specify the options, the runtime options of Ascent, we also create Conduit nodes. So in this case here, just to propagate errors, Python errors, we set that particular, we use that particular convention. We will open Ascent. We will publish the mesh, and then we need to define what to do. The visualization algorithm will be what we call the Ascent actions. So let me go step by step through this. We will define a node called action. To make a visualization, I will need a scene. I will need a mesh to display. I will need an algorithm, perhaps an ISO contour, extraction or slicing or streamlined extractions. We're going to make it simple for this example. We're going to do a pseudo coloring of the surface of the mesh. That's pretty simple. So there's no transformation of the mesh. In any case, I create a conduit node. I associate a particular scene in that node, and I set the type of operation I want. And the type is pseudo-color, and I want to choose a particular variable, and I will choose the bread variable. Now this might seem complicated, this particular syntax here, and you might say, how do I know all this? There's an API, and there's a whole lot of examples on the net, on the Ascent documentation, to actually, by examples, you can find the example that fits your need, and you will be able to do this. In summary, we create the actions, we define the scenes, and then we execute. That's the last part of our cell here. We execute Ascent given the particular action node. Okay, I ran out of time. So, interesting, actually. Am I out of time? Yeah, or not? Let me run it again. I don't know what's going on here. Those are standard examples that were developed at least a couple of years ago. I've run them 1,000 times without modification. They're the official examples from the tutorial. So I don't know why we're having trouble here this morning on I will stop this particular server and run a new one, because I don't have a good, I don't have an idea why this is. I know a couple of persons have experienced the same problem I just had earlier. Is this happening to other people? No, it's fine, okay. Okay, so in that demo of the Ascent tutorial, the first notebook, we defined a conduit node. We verified that the conduit node respects the blueprint convention. We create an Ascent action to pseudo-color the grid, and then we publish the mesh. We execute the Ascent node, and we get an image. And in the Ascent distribution, there's a very neat widget called the Ascent Viewer, which is dedicated to Jupyter. It allows you to browse through a series of images on your disk, and we use that in the demonstration, and we will use that also for the Catalyst demonstration, because it's very convenient. It's very convenient. Okay, now I'm back to my allocation. Let's run it again. Okay, here's my first cell created. I've printed my mesh. I execute my ascent algorithm. And as you can see here, as I execute the action, I actually here have again the description of my visualization algorithm in a Conduit node. So action, scenes, the first plot, it has a type, it has a field, it has another parameter called the image name. So this YAML description of the node is actually very convenient to visualize your algorithm. And the last cell which I mentioned is this ascent viewer, which will, given a particular an ascent node, will actually show on the screen here my image. You see, 5 minutes earlier it had crashed for no reason. I restarted the Jupyter notebook and now it works fine. So perhaps there are some issues with some compute nodes here internally. So this is it. This is our first demo. And when we're done with Ascent, we close. All right. Have you all been able to do this? Very good. So we will go to number 3, which goes through a number of blueprint examples. So we import Conduit blueprint.
Excuse me?
Yes?
Just as a curiosity, when you close Ascent, what is actually happening? So what is this closure?
By the way, I haven't really said, how does Ascent do its rendering? What's there? Ascent uses VTKM. Mm-hmm. VTKM is a C++ library which derives from the VTK C++ visualization toolkit library. VTKM actually is a new generation of the VTK toolkit, which addresses the issue of making code compatible with GPUs, accelerators, and all the modern devices we have around. So VTKM is an umbrella above the possibility to execute your code with CUDA, with TBB, with other acceleration techniques. So VTKM is hidden. We don't have to actually program with VTKM, but the algorithms of Ascent are actually implemented with VTKM. So when we close Ascent, what do? We actually shut down this rendering engine. And this rendering engine can be, as I mentioned earlier, can run either on the GPU or also on a CPU-only resource. And that's the neat thing about it. Furthermore, it also runs without an X window context, which is very nice. When we run a visualization application on our laptop, we use the rendering context with X windows, etc. That makes the compilation, by the way, pretty complicated. On PitsDaint, we have ParaView is an example where we have a compilation of ParaView using EGL. EGL is OpenGL without X windows. VTKM is something similar. We can do rendering without an X window system. So it's very convenient because we can launch it on any compute resources. So with the notebook number 3, we're going to look at a number of examples of the blueprint convention, and really import Conduit blueprint is a recommendation. If you try things by yourself and things don't work, it's possibly because your Conduit node does not conform to the blueprint. So I strongly advise you to run the blueprint test. So to create a uniform grid with a single scalar field, here we're going to explicitly create each parameters of the Conduit node. We declare a Conduit node called mesh. Those keywords here are specific to the convention. Okay, so the coordinate set has a type called uniform. It has a dimensions in x, in e, I, j, and k, which we set in this particular case. Because it's a uniform grid, you know that a uniform grid is defined completely by giving its origin and the spacing for each grid cells. So we have those encoded over here. Then we have the association of the scalar field. So here, the convention is such that under the fields keyword, you put the name of the variable. In this case, it's called alternating because it's 0 and 1. You see here the values in the numerical array are alternating between 0 and 1. So this is the name of the variable, and it's associated with the vertex. If we print that mesh, we will have what we see here on the screen, a coordinate set. It's a three-dimensional grid of size 9 by 9, and of course the numerical array here is pretty large for the screen. This is an array of 9 to the cube, which is pretty big, bigger than I can count. There we go. Here's the key. We verify that the mesh we have created conforms to the blueprint, and the result of the verification is another Conduit node called verify info. So if there is any problem with it, if you print that verify info node, you will be pointed to the place in the Conduit node that fails the verification. Otherwise, you're good to go and you can do your visualization. So this I have done. I will do, oh, not again. I will restart then. I have another crash. I don't know why. Name is not defined. Well, I'm sorry, I'm having some kernel crashes again. I don't know if you have more luck than me. Okay, let me go to, without executing actually the notebook, I'm going to go through the details of the next example, which is number 4, because it's pretty easy to follow anyway. We create a conduit mesh, a conduit node to represent a mesh, and that mesh will be a tetrahedral mesh. And here's an example where we will render different variables, and here's the definition. You will see how the definition of the scene is made. For the visualization pipeline, we create an action node where we add a scene, and we add 2 different scenes. So the first one we call S1 with the pseudo-color plot of the surface with variable var1, and we give it an image name, something related to var1, and then we add a second image, a second scene. It's always the pseudo-color variable, the pseudo-color algorithm, I want to say, with variable number 2, and we give it another file name. Once we execute this code, we should have 2 different images. So actually, I will try to do it. Here's what I can do. I can do those on my laptop. I don't know if it's Dane that's. This is very. Pardon me? So the option I have is to run those demo on my laptop. If you want to do, not this morning, but later on, you want to install Ascent and Conduit on your laptop. To run those demos, here's what I do, just to show you the setup I use. I need to make the window big enough for you to read. I set the Python path to my install directory for Ascent and for Conduit, such that I can import Conduit and import Ascent readily. In-situ. Comment no conduit. I'll get there. Just one more setup. Okay, so this is running on my laptop because on Pete's day I'm having trouble. Here's the result of the rendering of the alternating scalar field, so 0 and 1. Here's our image. It's a view, even though it's a 3D grid, because we're looking at it straight on, it looks like a 2D data set, but we will see later on how we can change that. Now, the Ascent Viewer widget actually enables you to see the image itself and the actions that were used to generate that particular image. So as you can see here, we have the conduit node description of the algorithm used to create the image. So pseudo-coloring of the variable called alternating. If I run the second example here, which is an unstructured mesh with two different fields, I will have the following image. So I have an unstructured mesh with two different coloring here for my particular pseudo coloring of the variable. And then finally, the example number 3. The example number 3 is interesting because it creates a time animation of a mesh. So we use this definition here. And the interesting thing is the definition of the node using always the blueprint examples. So we have again our mesh of 50 cube. Yes. We will execute that simulation. So now for each time step, I'm actually creating some example images using that particular algorithm, and then the result is seen in this particular widget, which if you play it will play the simulation as we go. So this widget we will use actually for the other demos, also for the Catalyst demos, because it's really, it looks at the images on the directory and animates those. If you pass them, in this case there's no action, so those are the 20 different time steps we have generated. This was number 3. And then for number 4, rendering with different scenes. I will show you the widget. So here's one scene, given that particular action, the pseudo coloring of variable number 1. And in the example 3 in the notebook is an interesting example whereby we modify parameters of the view. So it's a little bit, let me make it a bit bigger. There we go. We defined multiple plots. One of them is a pseudo color of variable 1. And here we adjust the camera. So here's an example where, following the convention of Ascent, and those examples are documented. I will show you the pointer to the page later on. Those are the ways to manipulate the camera, rotation, zoom, etc., with the different scenes. So for each of those, for those two renders, R1 and R2, we're going to execute our action, and I will show you the result with the next cell. Here's one, and here's second one. So what we have, if we look at the actions again, remember one of them was the zoom of the camera, the other one was the azimuth. Azimuth is an orientation in the direction that is circular around the object. So we have the two images here, the azimuth and the zoom. The example number 4 is about changing color tables. And here we have a name. All of you familiar with Matplotlib, you probably know the Inferno color map from Matplotlib. So this is available as well in Ascent. And the way to change that is using the specific key code color table, and we give it a name, Inferno, and we should have what people are familiar with. There we go. There is our classic Matplotlib Inferno color map. There, we close. So let me go back to my slides for a little bit, just to refocus a little bit on the presentation. I think it's actually worth it to look at a few slides from the SC11 tutorial. And that tutorial, that tutorial actually is there on the Ascent development website, and it's exactly those 9 notebooks which I have copied here to our PitchDaint repo which we are running. So there should be a pretty foolproof. However, this goes I'd like to go to the beginning if possible. Page 1. There we go. All right. So Ascent, in Ascent you'll have the standard representation modes, the pseudo-coloring which we've seen, the volumetric rendering, the mesh, the point also. You'll have the classic visualizations algorithms which you apply for scalar field, for example, isovolume, thresholding, slicing, contouring, and then you have a way to actually combine each of those. So you can very well, for example, use an isovolume followed by a clip. Okay, you can combine these in a Conduit node description. You combine all of those algorithms into your visualization pipeline. You can also do derived quantities. Here's an example of computing the vorticity, even though vorticity is a predefined operation in Ascent. Here is just the example that you can use it here. It uses the predefined gradient field to compute velocity. You can do time histories. You can do triggers. Here's something we've talked about it this morning. When it's too expensive to do a visualization step at each step of your simulation, you can very well say, for example, I want to trigger the visualization only every 50 time steps, for example. Or else you can trigger on a more complex operation. In this example, we trigger on a particular condition, which is the entropy, which is the difference in entropy between this current step and the previous step should be greater than 0.5. What does it mean? It means that something happens, the entropy has changed very much, so we need to trigger the execution of our visualization algorithm. And then in Ascent, we also have the extract. And one of the extract is actually, for example, writing HDF5 files. And this is actually one of my earliest motivation for using those in-situ libraries. Instead of having to learn an I/O library, if you describe your scene as a Conduit node, then Ascent can immediately save the result of your simulation in HDF5 in a format that is compliant with the Visit application software. So it's very convenient. Basically, for free, you have your I/O written into your simulation code. And I have one notebook which demonstrates exactly this. Here are some examples where Ascent was used at pretty large scale. Here's an example. This is from 5 years ago already, so you can imagine that today Ascent has been used in simulations that were even bigger. This was run at the time on 4,000 nodes in this fluid dynamics simulation code to run this particular visualization extraction. So this is a little bit the summary of what we've seen. We open Ascent, we publish the mesh, we execute the mesh. This is some info about how Ascent was compiled. This will tell you if the Ascent available is compiled with MPIs, with CUDA, with HDF5 output, and so forth. We've seen how Ascent uses Conduit, and those examples, the tutorial first slide is exactly the notebook number 1, which we have executed here on Pete's date. So this basically, I've gone through those little details on what each of the cells in the notebooks does. And I think this particular slide here is actually the most interesting because it combines together all the features available in Ascent, that is making images, which are the scenes subclass of actions, the pipelines, which transforms data or extract features. Extract is actually, in this particular meaning, saving data to an HDF5 file or passing data to a Jupyter notebook. The triggers, we've talked about an example of triggers, and then the queries is something that I probably should show you an example of to be more precise. So let me find the queries. I think is number 5. Transforming, capturing. Queries is number 7 in your notebook. So I'm running the first cell here, which imports Conduit and Ascent. And here's something interesting. In this particular cell, I have a time-varying mesh. So one of the things that's going to change is the value of the time step, the iteration number, and then the entropy of my field. So here's, you can see encoded here into this query, given the variable, this is the variable name, gyro, which is a scalar field. We compute the histogram of this field. This again is a predefined operation in Ascent. And then we compute the entropy of this histogram, given a default number of bins of 128. And then we render our scene. So here's the animation loop. For n steps, we're going to produce our mesh, update our mesh. The cycle is the iteration number, and we update the state of the mesh with that particular cycle. We publish the mesh, and then we set the image name to this particular file name. Now, when we do queries with time-dependent simulations, we have a node, actually a specific node, to retrieve the query results at the end of your simulation. So this is done here by instantiating a new Conduit node and then using the Ascent node, getting info about the runtime of the visualization algorithm. And if we do this, if we execute this query, I will show you now in a set of images here. Okay, here we have the animation in time. And then we retrieve the scalar field, the entropy of the histogram of our field, and then we do a standard matplotlib. Oh, guess what? I don't have matplot loaded here on my laptop. So there's always something. There's always something missing, but perhaps on Pete's Days you are able to run that exercise. I will try to fix this before this afternoon. There are two ways you can program an Ascent visualization pipeline. You can use JSON or you can use YAML. I prefer YAML because it's a lot simpler to look at. I always get lost with all those braces, etc. So this is exactly the same visualization task. One of them is encoded as a JSON file, one of them as a YAML file. Here's a pipeline description where I think we haven't seen one example yet where we add a pipeline with a given threshold on a scalar field. So those would be the parameters to use for the thresholding operation. And okay, here's something important here. We've seen the description of scenes with a pseudo-color of a particular variable, here called density. But what we had in the previous examples, we had the mesh itself without any transformation. However, in the previous page here, I have defined a pipeline. Instead of showing the mesh itself, I want to threshold it. So I have defined my pipeline called PL1. And this is what I specify here as a pipeline in my scene description. So if I were to remove this one particular line, I would have the three-dimensional view of my grid. If instead I use a pipeline, I will show the thresholded data with the same variable. So you can imagine now that this pipeline, instead of having only the threshold operation, I could have multiple operations. And in Ascent, this is how I would do it. I would define one pipeline with an operation called F1. And then immediately after, I would open a second set of braces with a different operation, which by default will take the output of the first algorithms and pipe it to the second algorithms. So here in your visualization pipeline, you can add as many filters as you wish. And then the last operation is to make the image, and you tell Ascent to make the image with the pipeline that you have defined. So to look at examples, I will be brief here. Pasc is one example where we have an SPH code developed in this Pasc project. Pasc is a consortium in Switzerland which supports the development of multiple projects for high-performance computing, and SPH EXA, co-developed here by CSCS, University of Basel, and are there other partners? Or just Zurich. And ETH Zurich, yes. SPH EXA is one of those examples. So it's an SPH code, so particles-only data. And if I look at the code, since it's particles only, I can drive you directly to the mesh definition of the code. You recognize here exactly the Conduit syntax which we've seen. So using the specific keywords for fields, here we add for each variable name, we had the name of the variable and the association, which is vertex, because we only have particles, so there's only one choice here. And then we shallow copy with the set external command. We shallow copy the pointers to the data representing the physics of the particles, so density, pressure, and so forth, velocity, etc. All those elements are encoded and passed via shared memory pointers. The mesh itself is defined over here. So using the code sets keyword, we set the x, y, and z coordinates of each particles, always using shared memory pointers. And those are the pointers, yeah. And then as you can see here, for all of those variables, x, y, z, velocity x, velocity y, velocity z, mass, etc., we add to the mesh description. And that's basically all we have. This fits in a couple of pages on the screen. In C++, the syntax to verify the mesh is this. We create a Conduit node called verify info, and we do this one call here to verify that we conform to the blue mesh. Once we have passed this particular check, we can publish the mesh and execute the action. And the actions for this particular case, I think, are defined just above. Here are the actions. We have particles, so one idea is to threshold particles by density. So this was the previous page example I had. In my pipeline, I define the threshold operator, density, minimum value, maximum value. I add this to the scene. Here's my pipeline, PL1, and I want to plot the density. And here, I've set a couple of cameras parameters, the look at point, the position of the camera, and the zoom factor. Now those are encoded into the simulation code by default. So by default, Ascent will execute, when we run the SPH simulation, Ascent will execute this particular pipeline. But we can override that completely if in the current directory where you run your simulation code, you have your own set of YAML descriptions for the Ascent pipeline, then this gets executed in priority. Okay, the scene I've shown you, and it's a total of 150 lines of code. Not bad if you think that with this you get also free I/O. You get all your data saved as HDF5 file. So that's pretty nice. Here's a bit more details, things that I've shown you already. This would be the YAML description corresponding to this set, to this code here, the X and Y and Z description for the coordinates of my particles. One scalar field, the density, the association via shallow copies. This would be the YAML example again. Same thing with coordinates, yeah. And we have, oh no, I'm going backwards here. And here we have the whole thing. I said free I/O HDF5. This is what you would do with 3 lines of code. Import the relay class from the Conduit library. Here's the about question or class, which comes from the info on the Ascent node. If the protocol HDF5 has been enabled at the compilation of Ascent, then you save your mesh, so you pass the Conduit node mesh and you give it a file name. And here you have a file that is compatible with the visit application library. Remember I told you that some of the developers of the Ascent code are from the team that developed years back the visit application. So this is why there is a one-to-one support for this particular format, the HDF5 blueprint. And this would be the content of the HDF5 file. It looks exactly like the description of your Conduit node. The important thing is that if you're running in parallel, all of this I/O will be done in parallel under the hood in a completely transparent manner. So that's very, very powerful. I have some supplementary code which I will leave for you as an exercise later on. This code, I have made 2 different versions of it. One of them with Python, so it's easy to demonstrate on a Jupyter notebook. The other one is the C++ version. It's parallel. It's parallel and it enables 4 different grid types: uniform, rectilinear, structured, or unstructured. You call it in this particular manner. You pass the mesh type as an argument. If, for example, we use the uniform mesh type, this would be the YAML description of your Conduit node. I think you're familiar with it now. There's the dimensions of the grid, the origin, the spacing, the topology, and then here the temperature scalar field. In the notebook that I have prepared over here, and by the way, those demonstrations which should run on PitchDaint, should also run, because they are mini applications, they should also run on your laptop after the tutorial today. So you're welcome to try again to run those particular demonstrations. With this particular notebook, my intent was to demonstrate the final feature of saving data to HDF5, and this is how you do it. With a Conduit node, you had an extract node with the relay type, and then you give it a file name, a path, and then a protocol. And as far as I know, at the moment, the Blueprint HDF5 protocol is the only one supported. Lulesh is another code, another demonstrations code where you can look in details at the mesh definition and the scene definition. It's an hydrodynamics code running in parallel. This is one image, one screenshot, which represents the velocity magnitude. This is a shock wave expanding from the corner of this grid out into the grid. Here again, if we look at the mesh definition or the scene definition, we can see things that are completely familiar. The sharing of all this information for the Conduit node, the description of, for each variable field of the mesh node, and for the interest of time, I will stop. I will not go further into those details. So this is also available on PitchDaint as a demo example. Maybe if you have some free time later on, you can try those in the notebook. Here's the exercise that I had planned to do. There are the instructions on how to compile on PitchDaint, and this is available. Actually, you can compile from the Jupyter notebook. You can compile that directly, execute the exercise, and instead of plotting the velocity magnitude, which I had seen in the previous image, here, I want you to plot, I suggested to plot iso contours of velocity magnitude. So this is an application of modifying the pipeline like we've talked about earlier. And as a hint, you can look at the tutorial pipeline number 5, which shows exactly how you can pipe multiple operations into your visualization pipeline. And I will click on this because this is one of the examples from the Ascent Read the Docs documentation. It shows you how, in my pipeline, I do a particular operation called contour, in this case, with a set of ISO value. And then I specify my pipeline over here in the description of the pseudo color test. Here's the resulting image. And this is the opportunity for me to show you the list of examples which are here on the left. There's a long list of examples of Ascent operations. Okay? So what I suggest for you to apply this to your own situations, you go to the Read the Docs document in the example section here, and then you search for keywords for the specific operation you would wish to apply. And really there's a long list of, here's an example of volume rendering. This is why we see this semi-transparent image. Each of those examples is there with the corresponding Ascent code and the resulting image. So it's very nice to look by examples for the operations which you want to apply. Here's an example of clipping with a sphere. And here's the result, okay? So if you have a supernova here in the middle, you want to clip, you can clip inside or outside of the sphere. So this would be exactly the operator to apply to your simulation. There, so Ascent, readthedocs.io, as they're all the examples you would wish to apply to your particular case. And I will stop here for this morning. We'll take a break. And then during lunchtime, you can tell me who has been able to run some of the examples, who has had trouble like I did. I don't know why. The Lulish example is a Fortran code, if I recall. And it's also part of the Ascent distribution. So if you install Ascent and later on Conduit on your own laptop using SPAC or using a standard CMake compilation process, you will get those examples also on your own compute platforms. Okay?